So today we're learning some new identities. They're called Sum and Difference Identities. Did everyone get one? Okay. The focus of these identities is a little bit less on proving things and more on evaluating. The identities, which we'll write down in a second here, you will have to memorize. The formulas are kind of long, but I'll help you guys memorize them. But here's the idea. The idea is we want to be able to find something like the cosine of 15 degrees. Is 15 degrees on the unit circle? Yes, it is not. All right, so no, you're right. Yes, I'm agreeing with you. Yeah, 15 degrees is not on the unit circle. But cosine of 15 could be rewritten as cosine of 45 minus 30. And I'll tell you why we would want to do that. Are 45 and 30 on the unit circle? They are. Now, it would be great if this was the same as doing cosine of 45 minus cosine of 30, but it is not the same. So don't ever do that, or I'll be extremely upset. But there is a formula for this situation. And the formula will allow us to find cosine of 15 by using the values for 45 and 30, which we do know. Let me put my little degree symbols in there. Okay, so let's look at the formulas. Let's learn how we're actually supposed to do it. So if we have sine of x plus y, two angles added together, or sine of x minus y, two angles subtracted, the pattern is the same for both. It goes like this: sine, cosine, cosine, sine, sine, cosine, cosine, sine. Leave a little space in there like I have. So this is step one to memorizing these formulas, is memorizing the pattern. That's what I'm showing you first. So we're just going to do a little chant, and you guys will do it with me in just a sec. But it just goes sine, cosine, cosine, sine. Sine, cosine, cosine, sine. You guys say that with me. Sine, cosine, cosine, sine. One more time. Sine, cosine, cosine, sine. So that's the pattern for sine. And by putting a little rhythm to it, you say that in your head every time you write it out, it's going to help you memorize it quicker. Think of how many lyrics to how many songs you know. Why is it easier to memorize that than like memorize books or passages of books? One's got rhythm and tune that goes with it. If you put rhythm to something, it's easier to memorize. Your brain accepts it better. It sticks in there. So every time you write this, sine, cosine, cosine, sine. Okay. Now, when we filled this out, the angles just alternate like this. So it's sine x times cosine y, cosine x times sine y. Whatever the two angles are, they just alternate as we fill them out. Nope. And then last but not least, there's a space in between them. That's on purpose. This one gets a plus sign and this gets a minus sign. And hey, that should be pretty easy to remember because look, there's a plus sign right there and a minus sign right there. So sine has the same sign. So, sine, cosine, cosine, sine. That's our sine pattern. Cosine has a different pattern. Cosine goes like this. Cosine, cosine, sine, sine. Cosine, cosine, sine, sine. Say it with me. Cosine, cosine, sine, sine. One more time. Cosine, cosine, sine, sine. Again. Cosine, cosine, sine, sine. What's the pattern for sine? Sine, cosine, cosine, sine. Okay. Say it, just chant it to yourself every time you do it. It'll stick. I haven't taught pre-calc in 3 years. I didn't even look at these notes ahead of time to refresh my memory. It's in there because of this rhythm. I was bad at this stuff in high school. I didn't even learn this stuff. It was dumb of me to not learn it. I could have learned it. I chose not to. But I still knew the pattern. I didn't know what it meant, but I knew the pattern because my pre-calc teacher kept saying it. And it bothered me, but it stuck. So it works, trust me. Okay, same deal here. The angles just alternate when we fill them out. Cosine has the opposite sign in the middle. And so I like to use the O in cosine to remind me that it's opposite. What's my spell check telling me? That's so silly. Okay. We'll come back to tangent. Tangent's a little bit different. Do some practice with this first. So we'll go down here to our example. So it's not this. But if I rewrite 15 using unit circle angles, that's our first step. Then the next step is to expand using the formula. And then the third step is to evaluate. So for cosine, what's the pattern? Cosine, cosine, sine, sine. Cosine, cosine, sine, sine. Our angles are 45 and 30, so here we go. 45, 30. 45, 30. What goes in the middle? Plus. For cosine, it's opposite. Okay. So, step 1, check. Step 2, check. Now we evaluate. Just like it's unit circle. Root 2 over 2. Root 3 over 2. Plus. Root 2 over 2 times 1/2. So you gotta be nice with the unit circle to be able to do this, which is why we reviewed it today. Okay, turn to your neighbor. What does that equal? Using math. Talk about it. Okay, that is root 6 over 4. Root 6 over 4. When we multiply fractions, we multiply the top and the bottom. This is plus root 2 over 4. Now, when we're adding fractions, we keep the denominator the same. So what this is root 6 plus root 2 over 4. And that's our final answer. We can't add root 6 and root 2. They don't have the same base. We can add 2 root 2 and 3 root 2 and get 5 root 2. We can't do it with root 6 plus root 2. So that's our final answer. Your answer is always going to look something like that. Combination of root 6 and root 2 over 4. If you're doing sine and cosine with something from the unit circle. Or using unit circle angles. Okay, with your neighbor, talk about number 2. How can we make this 2 angles added or subtracted? Talk about it. Okay, what angles could we use? I heard it. 45 plus 120. Did anyone do anything different? What would you do?
135 plus 30.
Yeah. Okay. Anyone do anything different? Okay. 225 minus 60 would also work. There's some other ones too. There's always going to be more than one way to combine, and we're going to get the same answer for both of these. Okay, so you can just pick whichever one you want. It doesn't matter. I'm going to do both. We're going to expand these. What's the pattern for sine? Oh, sine, cosine, cosine, sine. That's right. Sine, cosine, cosine, sine. What goes in the middle? Plus. Okay. No matter which way we do it, we should get the same answer. Root 6 minus root 2 over 4. You can also write that as negative root 2 plus root 6 over 4. It's the same thing. But no matter what, we'll get the same answer. Even if I did 225 minus 60, I would get the same thing. It'll always work out to be the same. And like I said, it's always going to look something like this. Some combination of root 6 and root 2 over 4. Both positive, both negative, one negative, the other positive. As long as we're doing angles that can be made up of unit circle angles like those. So that's the process. It's pretty straightforward. It basically works the same way every time. There's another type of problem that we're going to see with sum and difference. So let's go to the back. So now we've got 2 angles, alpha and beta. These are not unit circle angles, but they're the kind of angles that we would draw a reference angle for using a triangle, like we did on the Unit 4 test last week, which didn't look great, by the way. We'll get those back today. So here's alpha. I struggle with alpha sometimes. Hold on, here we go. If the sine of alpha is 3 over 5, that means the y is 3 and the hypotenuse is 5. It's in the first quadrant because I'm told that theta is between 0 and pi over 2. Beta is also in the first quadrant, but I'm going to draw a separate triangle just so we don't get these mixed up. cosine is 5 over 13, that means x is 5 and the hypotenuse is 13. Okay, turn to your neighbor. What are the missing sides of these triangles? Okay, what are they? 4 and 12. Yes. So just go ahead and memorize these triangles. Your geometry teacher told you the same thing. These just come up all the time. 3, 4, 5 triangle and any multiple of it. 6, 8, 10, 12, 9, 12, 15, etc. And 5, 12, 13. Just memorize them. You're going to see them a lot. In AB Calculus 2 days ago, 3 days ago, 4 days ago, whenever it was. These triangles came up. They have a test tomorrow. No spoilers, but there's going to be these triangles on their test. Got to memorize them. Makes your life easier. Okay. So we have our 2 triangles, and we're trying to find, this is written incorrectly here. This should say alpha plus beta. It shouldn't just say A plus B. Should use the same variables. But this is the same idea. These aren't unit circle angles, but we have the information that we need. We're going to expand. Sine, cosine, cosine, sine. We're going to alternate. Alpha, beta, alpha, beta. Alpha you can kind of draw like a little fish. Like that. What goes in between? Plus. Yeah, sine has the same sign. Okay, what's sine of alpha? Yes, 3/5. Okay, be careful. Do not write sine of 3/5. That's not correct. That is a different thing. We know the sine of alpha. It equals 3/5. We replace the whole thing with 3/5. What is cosine of beta? 5 over 13. We were given that information, but we can also see it on the triangle. What's cosine of alpha? 5 over... Wait. Cosine of alpha is what? 4 over 5. And sine of beta is... Okay. So we're just looking at these triangles like we're back in geometry. Opposite over adjacent. Or opposite over hypotenuse, adjacent over hypotenuse. Just looking at the triangle there. Okay. We need to simplify this. Some of you might be thinking, oh, we can cancel out the 5s here. You're right. We can do that. But we don't want to, actually, because right now they have the same denominator of 65, so we're just going to add these fractions. This would be 15 over 65 plus 48 over 65. And so we just get 63 over 65. Something we're not going to look at in this class is where this formula comes from, like proving why it exists. We're just going to use it. If you're interested in seeing why it's true, you feel free to come to Warhawk Time. I can show you. It's a little bit elaborate. It's not super crazy, but it takes a little bit of time. So we don't need to worry about where it comes from. We just need to worry about using it in this class here. Okay. Let's look down at number 5. Notice the directions. What are we told to do in number 5? Condense. Okay, that's the opposite of expand, right? Just like with logarithms. What we want to do is we want to look at this and recognize the pattern. What pattern do you guys see here? Yeah, cosine, cosine, sine, sine. Okay, so this is the expanded version of cosine. Of two angles subtracted or added? Subtracted. Which two angles subtracted? Yeah. So we're just rewinding here. What is 85 minus 25? 60. What is cosine of 60? One half. Okay, so sometimes we just want you to work backwards. Basically just more reps with the formula. Okay, I want you guys to try number 6. This is the same process as number 1 and number 2. So give that a try. Work with your neighbor. Okay, pause for a sec. I'm seeing two things mostly, and yeah, one of them is this. Does pi over 6 plus pi over 6 equal pi over 12? Is 1/2 plus 1/2 1/4? No. Okay, so we can't do that. That math is not good math. Okay. The other thing I'm seeing, which is a good approach, is to convert this to degrees. I don't hate this approach, but I'm going to ask you to not do it again. But let's just talk about it. If we convert this to degrees, how many degrees is this? This is 15 degrees. We already did 15, so we could make this cosine of 45 minus 30, like we did on the other page. Okay, this is a good idea. Again, I don't blame you. Just don't do it anymore. Let's think about this. Let's think about keeping this in radians. What is the what's 45 degrees in radians? And what's 30 degrees in radians? Pi over 6. So this is how we want to expand it. Okay, if we are looking at these angles here, let's look at our first quadrant angles for a sec. Pi over 6, pi over 4, pi over 3, pi over 2. What's the least common denominator of those angles? 12. Yeah. Pi over 6 would be how many over 12? Yeah. Pi over 4 is? Pi over 3? And pi over 2? Yeah. So if you're seeing 12 as a denominator, it's just our angles in radians with a common denominator. So when we do pi over 4 minus pi over 6, it's just 3 pi over 12 minus pi over 12, which is just 1 pi over 12. So that's what we're doing here. Okay, go ahead and expand that the rest of the way and solve it.
Mr. Bowden.
Yep.
Number 3. The condensing, how did we get that?
We basically recognized the pattern, that it was cosine, cosine, sine, sine. And so that means it's cosine of two angles subtracted from each other. So then we just subtracted the angles. Did you guys get root 6 plus root 2 over 4? Could also be root 2 plus root 6 over 4, same thing. So you're going to see a lot of questions where the denominator is 12. It's something pi over 12, like 7 pi over 12 or 11 pi over 12 or something like that. That's just these angles here, your unit circle angles with a common denominator. So just keep it in radians, don't change it to degrees, and then do the problem the same way. Okay, how are we doing? Any questions? All right, time for some tangents. Let's go back. So tangent has a different pattern. Here's what it looks like. Okay. So notice the angles are alternating, just like before, x, y, x, y. We have two tangents added together on top, and then on the bottom the two tangents are multiplied, and they're subtracted from 1. On top we have a plus sign, on the bottom we have a minus sign. So remember that tangent is sine over cosine. And so for our plus sign and minus sign here, we have the same sign on top, because that's what sine does. And we have the opposite sign on the bottom, because that's what cosine does. So our tangent for difference is tangent minus tangent, 1 plus tangent tangent. Okay. And here's our pattern. It's silly sounding, but that's okay. You'll remember it. Tan tan, 1 tan tan. Tan tan, 1 tan tan. Say that with me. Tan tan, 1 tan tan. Tan tan, 1 tan tan. Oh, tan tan, 1 tan tan. Tan tan, 1 tan tan. Silly, but it works. Okay, process is the same, tangent, objectively harder. Way more simplifying that we got to do. So I guess that's good news and bad news. Bad news is it's harder. Good news, we're going to do it right now. So, 75 could be what? 2 angles that we know. Okay, yeah, we'll keep this in degrees. Because it's in degrees. Yeah. Yeah. And, you know, the order doesn't matter. 45 plus 30, 30 plus 45. Doesn't matter. Okay, so we're going to expand. And when we expand, we get... Yeah. Tan, tan, 1 tan, tan. Say it like you mean it. Tan, tan, 1 tan, tan. 45, 30, 45, 30. On top, we're going to have plus or minus. And on the bottom? Minus. Okay. If you remember the pattern, sometimes what students get confused with is where the plus sign and minus sign go. If you remember the pattern, there's only one place that they can go. It's got to go in between the two tangents. It wouldn't make sense to put a plus sign anywhere else. And same thing here, the plus sign or the minus sign has to go between the 1 and the other things. Because it wouldn't make sense to go in between there. Then the 1 would have nothing to do with this. So they're added or subtracted on top. The tangents are multiplied on the bottom. That's where they go. Okay, tangent of 45. 1 plus tangent of 30. Root 3 over 3. Okay, because that's pi over 6. So we learned our shortcuts. Now we know them. 1 minus 1 times root 3 over 3. So I just rewrote it without the 1 multiplying in there. Okay, we got to do a couple things to simplify this. The first thing we're going to do is find a common denominator. What's our common denominator going to be? 3. So we'll just make this 3 over 3, and that one 3 over 3. And then once everything has the same denominator, what can we do? Cancel them out. Okay, now remember, if it's 1/3 minus 5/3, you cannot cancel out those denominators. We can only cancel out the common denominator when it's fractions divided by fractions. But then we are allowed to do it. Boom, 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 boom. So 3 plus root 3 over 3 minus root 3. Sometimes it works. All right. Still not done simplifying, but we've gotten rid of the fractions over fractions. What do we need to do to simplify that? Yeah, we have a radical on the bottom. We need to rationalize. What do we do? Not multiply by root 3 over 3. Not multiply by 3 minus root 3. Very close. No. 3 plus root 3. Yes. 3 plus root 3. So what this is called is multiplying by the conjugate. It's opposite from what's on the bottom. Changing the sign in the middle. So we need to FOIL the top and bottom, or double distribute, or multiply it out, however you want to think about it. So on top we get 9 plus 3 root 3 plus 3 root 3 plus 3. On the bottom we get 9 plus 3 root 3 minus 3 root 3 minus 3. Don't use the box method for this. That takes too long. For something like this, you just got to be able to do it. 3 terms, box method's fine, but not for this. It's too inefficient. We're going to combine like terms on the top and bottom. So on the top we get 12 plus 6 root 3. On the bottom we get 6. Those cancel. 9 minus 3 is 6. Can I cancel out these 6s like that? No, not unless I also do what? Do it to the 12 as well. This is the distributive property. I'm dividing both of these by 6. This is the same as like 1/6 times 12 plus 6 root 3, if that helps to think about it that way. But the distributive property works with division. You just have to divide both things. So this is 2 plus root 3 when it's simplified down all the way. Who knew that what we started with could simplify down to 2 plus root 3? You knew? Nice. I also knew because I did it in second period today. Yeah, tangent, you're just always gonna have to do way more simplifying. Just so you know, just get your expectations. Set your expectations. You guys do number 4 on the back. Ready, set, go. You guys are doing great so far. The main difference between this one and the last one is you're not going to have to rationalize because these are all fractions. You still will need to find a common denominator. Make sure you label your 2 triangles. That's one thing on the test that I'll be looking for. So I've got A and B. All right, we'll check that when we get back from lunch. Some people do it the right way. I just saw a lot of different fractions come out of this.
Yeah, I feel like I did that so wrong. I don't know what I messed up on.
Because you would multiply by the reciprocal.
Yeah.
That's okay. The right one. You got
Did you subtract?
16 over 60. You have to add it.
Okay, that's definitely a lot. Yeah. So thank you. Yeah, we did something wrong. That's okay.
Yeah, the tans on the bottom are the tans on the I think the top is good for this one. That's okay.
Okay, so let's just check here. Looks like maybe arithmetic was the problem. Tangent A minus tangent B over 1 plus tangent A times tangent B. What is tangent of A? And tangent of B? Yeah. So what's nice about tangent is you only need 2 things, 2 different tangents. Okay, so we're going to find a common denominator here. Again, make sure that you're not writing tangent of 12 over 5. That's not what we want. The tangent of A is 12 over 5, so just replace it all the way. What's our common denominator going to be? 15, yep. So multiply that by 3 over 3, this one by 5 over 5. That one's 15 over 15. So we get 36 over 15 minus 20 over 15 over 15 over 15 plus 48 over 15. You can add those fractions now and keep the denominator the same, or you can just cancel out all the denominators right now. So we're left with 36 minus 20 over 15 plus 48. So that's how we get 16 over 63. Questions on that process? Okay. Hopefully what you guys are noticing is that when we're using the sum and difference formulas, it's a very straightforward process. It's very clear when we're supposed to use it. Find tangent of A minus B. Or we're trying to come up with something to make an angle, to find 2 unit circle angles that add or subtract to an angle that we're looking for. Usually for an example like this, we'll even tell you to use sum and difference. So it's pretty straightforward. You just have to expand the formula, plug in the values, and simplify. We'll look at the last 2 questions here on the back, proving the identities, and then we'll use that as a segue into our going over our quiz from last class. So similarly, in a proof with sum and difference, if you take a look at it here, it should be obvious that we need to use sum and difference. What makes it so obvious is this thing right here. This is weird looking. Weird looking. Just like you guys were in middle school. We got 2 angles added together, right? It's pi over 2 plus theta. I was weird looking in middle school too. We all were. That's strange. We don't see that in proofs. Okay, so I see a plus sign in there. Oh, let me expand this. What's the pattern for cosine? Cosine, cosine, sine, sine. So pi over 2, theta, pi over 2, theta. And what goes in the middle? Minus. Yep. So now we're going to evaluate. Theta is just a variable. So cosine theta, sine theta, those are just those things. Like x and y are just x and y. We can't figure out what cosine theta is. But we can figure out what cosine of pi over 2 is. What does that equal? 0. Yeah. So this is 0 times cosine theta minus, what's sine of pi over 2? So this is minus 1 times sine theta. Well, that equals 0. 0 times anything is 0. So this is just negative sine theta. And then it works out. These proofs will never be super complicated. They're pretty straightforward. Just expand and substitute. Go ahead and expand the other side. All right, so we use our tangent formula, tan, 1 tan. What's tangent of pi? 0. So this just becomes 0 minus tangent theta over 1 minus 0. So it's just negative tangent theta. So that's how you do sum and difference.